Welcome to the deep dive. Today we're doing something really foundational. We're not just looking at the results of studies. We're going deeper into the mechanics of how researchers get that information in the first place.
Exactly.
Because if you really want to be well-informed, you have to understand the architecture that's holding up the data.
That's absolutely right. The source material you shared gives us a really clear roadmap to, well, what you could call the twin pillars of social science.
Okay.
First, there's observation, which is about how we accurately see what's happening. And second is sampling, which is all about how we pick a valid, a manageable piece of that reality to study.
And our mission today is to unpack both of those.
Yeah, focusing on how choosing the right method, or I should say the wrong one, can completely change the validity of your findings.
Okay, let's unpack this then. Let's start with what seems like the simplest act, just watching. How do we take observation from, just looking at things and turn it into real scientific data collection?
Well, the sources define observation as a method that gives researchers live data from situations. And that term, live data, is so important.
Live data. Why that phrase?
Because it lets us bypass what's called perception-based data.
So we're getting around self-reporting. It's like the difference between asking someone, do you think you're a good driver, and actually sitting in the car with them.
Exactly. Observation isn't about what people say they do or what they think. It's about what they actually do. And this gives it a huge advantage. One of the sources, Huaj Lee, points out that it helps eliminate the bias that people might introduce if they know they're being, judged on their perceptions.
You capture authentic behavior.
In its natural context.
So it's almost like a shortcut to someone's personal knowledge, right? The things people just do without even thinking about it, things they might not be able to explain in an interview.
Precisely. And it gives you all this rich, descriptive information about the entire setting. But, and this is a huge but, this power comes with a major catch. You can't just passively watch. The material really hammers this home. For it to be scientific, you absolutely need an observation framework.
Why a framework? I mean, we all observe things naturally every day. Why does it need to be so structured?
Because without one, your live data is really just a collection of anecdotes.
I see.
The framework makes sure three things happen. First, that all the observers are focused on the exact same activities. So maybe you're only tracking who interrupts who, not the content of the conversation.
Got it. Consistency.
Second, that the data is recorded systematically using some kind of predefined codes. And third, and this is the most critical part, that the data is consistent between observers.
So if you and I watch the same meeting, our notes should basically line up.
They have to. If they don't, the method is just. It's unreliable.
Okay, so observation gives us this amazing tool for capturing what's really happening.
Yeah.
But then we hit that wall, the one that every researcher hits. You can't study everyone everywhere. And that brings us right to sampling.
It's the ultimate practical constraint, isn't it? As one of the sources confirms, trying to study the total population, every single customer, every student, it's impracticable.
Impracticable.
Yeah, because of cost, time, all those logistical hurdles. So sampling isn't just a nice to have, it's an indispensable technique that makes research possible.
So when we talk about a sample, what is this slice of reality we're actually taking?
The definitions in the material are really consistent on this. One calls it a fragment of the total phenomena. Another one sums it up as selecting a few from a bigger group to, estimate or predict what's happening in that bigger group.
And this gets to the very heart of how science works, right? This idea of inductive thinking. We look at something specific, our sample, and then we make a general claim about the whole population. We generalize.
Exactly. The numbers we get from our sample, those are called statistics.
Okay.
So if we measure the average job satisfaction in our sample, that's a statistic, but we then use that number to make a much bigger claim about the satisfaction of the entire company.
And that's where the danger is. If our slice of the pie isn't a good representation of the whole pie, our generalization is, well, it's garbage.
It's utterly compromised, and this is the key takeaway here. The accuracy of your generalization depends entirely on sample representativeness. A good sample has to be a mirror image of the population, just smaller.
Which brings us to another element the sources highlight. What makes a good sample?
Right. It's not just about how you pick it. A good sample has a few key characteristics. It has to be representative, like we said. Its precision must be measurable, and it has to be adequate in size.
Okay, adequate in size. How do you figure that out? That seems tricky.
It is. That's a whole field of study around sample size. We can't get into all the complex math today, but the principle is what matters.
And that is?
It has to be big enough to minimize what's called sampling error, but small enough to actually be feasible. It's a constant trade-off. The more precision you want, or the more varied your population is, the bigger your sample needs to be.
So we've got the big picture. We know why we have to sample, and we know the sample has to be representative and big enough. Now let's get into the weeds. The core divide. Probability versus non-probability sampling.
This is the fork in the road. This one choice basically defines what kind of claims you can make at the end of your study.
So let's define them. What is probability sampling?
In probability sampling, sometimes called random sampling, every single unit in your population has a chance of being selected. And it's a chance that's greater than 0.
A calculable chance.
A calculable chance. Because we know that probability, we can mathematically figure out the margin of error. That's what makes our generalizations statistically reliable.
That sounds like the gold standard. So what's the other side of the coin?
That would be non-probability sampling. And here, the selection is based on other things, like the researcher's judgment or convenience or people just volunteering.
And the big problem with that is?
The big problem is that an unknown portion of the population is completely excluded. And because you don't know the probability of selection for each person, you simply cannot know how representative your sample is. The generalization is on very shaky ground.
This is where it gets really interesting. Okay, let's dive into that gold standard first, probability sampling. Let's imagine a scenario. We're studying, say, 1,000 employees at one big tech company to see how efficient their internal communication is.
Perfect example. So the most straightforward method is simple random sampling.
Simple random, like pulling names out of a hat.
Pretty much. The population is small, it's homogeneous, we have a list of all 1,000 names, so we can use a random number generator or a lottery system to just pick, say, 100 names.
And every single person has an equal shot.
An equal known chance of being picked. It's very clean.
But what if that list is already ordered, say, alphabetically? Is there a more efficient way?
There is. That's where systematic random sampling comes in. It relies on that ordering and a fixed interval, which we call K. So if we need 100 people from our 1,000, K is 10. We pick a random starting number between 1 and 10. Let's say we pick person number 6, and then we select every 10th person after that.
So number 6, then 16, then 26, all the way through the list.
Exactly. It's often faster than a random number table, but it still achieves randomness.
But hold on. What if our tech firm isn't homogeneous? What if it's, say, 700 staff, 200 managers, and 100 senior executives? If we just sample randomly, we might get almost no executives and way too many staff members.
And your findings would be completely skewed. That's the exact problem that stratified random sampling is designed to solve.
Stratified. So we're talking about strata or layers?
Precisely. You divide the population into those distinct categories, staff, managers, executives. You treat each of those strata as its own little population, and then you do your random sampling within each group.
Ah, so you guarantee you get the right proportions.
Yeah.
If executives are 10% of the company, they'll be 10% of your sample.
That's called proportionate stratification, yes. But here's where it gets really powerful. You can also do disproportionate stratification.
What does that mean?
Well, let's say you know that the views of those 100 executives are absolutely vital, but they're a tiny minority. You can choose to sample a higher fraction of them than their proportion suggests.
So you oversample them on purpose. But isn't that just bias? Aren't you putting your thumb on the scale?
It feels like it, but it's not bias because the probability is still known and calculated. You're making a deliberate choice. Then, in the analysis stage, you statistically weight their responses back down to their true proportion.
I see. So you get enough data from that small, crucial group, which a simple random sample might have missed entirely, but you don't let it distort the final results.
You've got it. It's a tool for ensuring you hear from the minority voices.
That's a clever tool. Okay, now let's make our scenario more complicated. That tech company isn't in one building anymore. It's global. 10,000 employees across 10 different cities.
Right.
Randomly sampling 100 people across 10 countries. That sounds like a logistical and financial nightmare.
It is, and that's where cluster sampling comes to the rescue. This is all about efficiency. It's a two-stage process.
2 stages.
Stage 1. You randomly select a sample of clusters. In this case, the clusters are the city campuses. So maybe you randomly pick 5 of the 10 cities.
And stage 2?
Stage 2. You study all the employees within those 5 selected clusters. Or you could do another random sample within them.
Okay, the big advantage there is obviously cost. You're not flying researchers all over the world. You only have to go to 5 cities, not 10.
Exactly. It cuts down on travel, administration, all of it. And if you need to get even more complex, like randomly picking countries, then cities within countries, then departments within cities, that's when you move to multi-stage sampling.
It's like clusters within clusters.
It is. And you use it when a complete list of every single person in the whole population just doesn't exist.
Okay, that makes a ton of sense for the probability world.
Yeah.
But sometimes reality just forces your hand and you can't use these controlled methods.
Right.
So now we had to cross that line into the world of non-probability sampling.
And this is where we have to be so careful about the claims we make. Let's start with convenience sampling. It's also called grab or haphazard sampling.
Sounds sloppy already.
It is, in a way. You're just drawing your sample from the part of the population that's close to hand.
Like standing outside the cafeteria at lunch and interviewing the first 50 people who agree to talk.
That's a perfect example. It's fast, it's easy, but it is deeply flawed if you want to say something about the whole company.
Why flawed?
Because you simply cannot scientifically generalize from that sample. Who eats lunch at that exact time? Who is willing to stop and talk? They're inherently unrepresentative. And the sources specifically note this method is not useful for pilot testing either.
Interesting. Why not for a pilot test?
Because if your pilot sample is already biased, you learn nothing reliable about how your questions will work with the real population you want to study.
Makes sense. Okay, what's next?
Next is purposive sampling. Here, you're picking your sample based on very specific criteria that are important to your study.
So this is more deliberate.
Very deliberate. The researcher uses their own judgment to select people they know have certain characteristics. If you're studying a new piece of software, you might only sample the lead engineers who designed it. It's about targeting expertise.
And finally, there's the one that often trips people up, quota sampling. It looks a lot like stratified sampling, but it's not.
It's so deceptive. It starts the same way. You segment the population into groups, say, by department.
Right.
But the next step is where it all goes wrong.
How so?
In stratified sampling, you randomly select people from each department. In quota sampling, the researcher just finds people to fill the quota using their own judgment or convenience.
So you stand at the entrance to the engineering floor and just grab the first 20 people you see to fill your engineering quota.
Exactly. And you might subconsciously pick people who look friendly or less busy. That judgment call, that convenience in the second step, completely kills the randomness. It's an easy technique, but the sources are clear. It is not a representative sample.
You've traded reliability for speed.
At the end of the day, that's the trade-off with all non-probability methods.
So if we zoom out from all this, we've really covered the whole flow. Observation gives us a systematic way to see what's actually happening in one place and time.
Right, but it needs that rigid framework to be consistent.
Then sampling becomes essential when we need to generalize from that specific observation to a whole population. And that forces this huge choice.
The choice between the calculated defensible risk of probability sampling.
And the convenience, but deep limitations of non-probability sampling.
The difference really does hinge on probability. If you need to make claims about a population where you can stand up and defend your margin of error, you have to use a probability method. There's no way around it.
And we also saw that it's not just the method. A good sample needs that careful thought about its size and characteristics to make sure it's a true miniature version of the whole.
It all comes back to control, doesn't it? The more control you have over the method, the more reliable your results are.
So here's a final thought. We learned that an observation framework is absolutely necessary to make sure that data is consistent between different observers. So if the method for just gathering live data needs that much control to be consistent across people, what does that tell you about how tightly you have to control your sampling process, the actual selection of your data, if you want your statistics to hold up, not just now, but across time and across different, constantly changing populations?
That's a powerful question.
That's something to mull over until next time.